You've seen some of the basic ways that we can use lists in Python to give us sort of sequences or groups of data. But in fact, Python lists are very, very powerful and have an interface that, for many people, makes them very easy to do kind of complex things with. So let's look at some examples of the kinds of things that you can do with lists and some of the features of lists in terms of how they are built and work and things like that. So you've already seen that lists are collections of values, and you may have seen some examples where they can be added to, possibly somewhere they can be removed from, but there are actually lots of ways to do these different behaviors here. Here are a few examples. So we can take a list and we can call the append function, and that adds some single item onto the list. We also can do addition with lists. For instance, we have our existing list L, and we say L plus the list that contains 7. It will take whatever L currently has, so that's this sequence of numbers here, 4, 3, 12, 9, and the 5 that was added in the line above, and then it adds the list containing 7 to it, combines those two lists, and makes the list 4, 3, 12, 9, 5, 7. It's also important to remember that lists have an order, and that's the order that the items are given to them. Not necessarily sorted order or anything like that, but just the order that was established. They stay that way. And when you add new things on, they're going to be added sort of in sequence one way or another. And here you'll notice that we are saving the result of L plus the list containing 7, and we save that as L again. So that replaces L with this bigger version of it. If we just said L plus the list containing 7, that would create a new list, but it wouldn't necessarily save it anywhere. Whereas doing append actually changes the list L without having to say L equals again. This is something that you'll want to kind of get used to, that calling functions on your list may change the list. You don't have to say L equals necessarily there. But when we do stuff that looks like math, just like when you say x plus 3, it doesn't change x. It gives you a new result of whatever x was with 3 added to it. To save it, you have to say something like x equals x plus 3. And the same is true for lists. A statement like L plus the list containing 7 creates a new value, that new list, but it doesn't necessarily store it anywhere. So always remember to store the results if you want them to be saved as some variable. In another example of using a function, there is remove. And so if we say L.remove 12, it will remove the first instance of the number 12 that it finds. So it looks through, it finds the number of 12 as the third item and removes it, and you'll notice all the other items stay in the order that they were. It does not leave empty spaces. We cannot really have empty spaces in our lists, and that's something, again, that you'll have to keep in mind, that when you remove things, the locations of stuff changes. And that's particularly important because items inside our lists have an index. That is a number that indicates where they are in the list. The first item will have index 0. You'll find computer scientists often like to start with 0 as the first value, not 1 like you might do in other settings. So here we've created the list L. It has 4, 3, 12, and 9. So the index of 4 is 0. The index of 3 is 1. The index of 12 is 2, and the index of 9 is 3. You'll notice I'm able to get the items from the list, and this is very, very important, a feature that you'll use quite commonly. I can get the items from the list by using square brackets and then giving the index inside of there. So this is asking for the item at index 0 from the list L. And then if I printed it out, that would print out the number 4 because it's the item at index 0 in my list. Likewise, if I say L square brackets 3, then I'm asking for the item at index 3 from the list L, and that is the number 9. Now, there are other interesting ways to get to items. So you'll notice that when I use the 0 and positive number version, that's kind of moving left to right with my indexes. If I want to move right to left, then I can use negative numbers. So index -1 is not something that comes before the item at index 0. In fact, it's allowing me to start from the end and go back 1. And so that is also 9. So 9 kind of has 2 indexes, and everything in your list will kind of have 2 indexes. 9 has index 3, if we're going positive numbers, and it can be accessed by index -1 if we're going negative numbers backwards. I could access the number 12 by using the index -2. I could use the index -3 to get to the number 3 here, and the index -4 to get to the number 4. There is no -0, so we can't use the same numbers in the same way. We have to start with -1 when we're going the opposite direction. If you try to get something at an index that is not valid for your list, for example, here the valid indices are 0, 1, 2, and 3. There is nothing at index 4 right now. And so if I tried to get the item at index 4, Python will give me errors, in fact, and specifically index errors, and tell me that my list index is out of range. The same would be true if I used negative values that were too far negative. Now, if I added another item onto this list, like the number 5, after the number 9, then index 4 would be valid, and I would get back that 5 as my result. So again, remember that when we add or remove from a list, the available indexes will change. We can also check for containment, and we can specifically find the index of values inside of our list. So I can ask for the index of 3 in my list, for instance, and it will tell me that 3 is at index 1. I can ask if things are in my list, and it will give me back a true or false. These are very helpful in if statements or in loops, for instance. And if I ask for the index of something that is not in the list, then I will get a value error, and it will inform me that that thing is not in the list. This is why it might be important to check if 7 is in the list first, and then try to get the index of 7, for instance. Another really powerful thing that you can do with lists in Python is you can select portions of the list by index by providing the indices to start with and or the indices to end with. And I'll show you a few different examples because you can do this in a lot of different ways. So again, if I have this list 4, 3, 12, 9, then I can give sort of like a lookup statement, sort of like the ones where I was getting the index for just a single number, but I put a colon in the middle of 2 numbers, and that tells it where to start and where to end. And this is a pretty straightforward way to get a chunk of my list. The only tricky part, typically, is remembering that the start value is included and the end value is excluded. So when I say indices 1 through 3, it gives me the number 3, which is at index 1, and it gives me the number 12, which is at index 2. It does not give me the number 9, which is at index 3. So, for instance, if I said L1:1, that would give me a list that only contains the number 3. It's still a little different than just saying L(1), because the result, you will notice over here on the side, will be a list. It could be a list that contains only one item. It could be a list that contains a large number of items, but it will be a list. So this is one thing to be careful with if you are programming in this way, is remembering that even if your range only includes one item, the result you get back is a list. And so you won't be getting a number back. So be careful not to say, try to add a number to that, or try to subtract it or divide it or things like that, because your result will be a list. And you can only do with it the things that lists do, not necessarily the things that numbers do. So that's the most sort of standard way to splice a list, to take a subset or subsection of the things that are in that list, is to give it a start index and an end index. But you also can give it just the end index or just the start index. When you only give it an end index, it sort of fills in that what you meant for the start was index 0. And so it will go from the start of the list up to whatever your end index that you provide there is. So this is shorthand for saying L0:2, because it takes the item in index 0, it takes the item in index 1, but it does not take the item at index 2. So again, the end is still excluded. So this allows me to get up to some stopping point. And on the other hand, if I provide only the start index, then it will go from that start index all the way to the end of the list. So here, this gives me the item at index 2, which is 12, and the item at index 3, the last item in the list, which is 9, and then it ends my list because there's nothing left to grab. So these are the sorts of statements, all of this splicing stuff, are the sorts of statements that could take a somewhat complicated for loop or that kind of thing to grab the items out of your list, but you can do it in just one line to split up the list and get just these portions here. And similarly, I can use negative indexing to tell my statement how far back into a list to step. So for instance, here I provided the end index -1. Since the index -1 refers to the number 9, then that number will be excluded from my list that results. So it gets from the start of the list up to but not including the item at index -1, the last item in my list. So I get 4, 3, and 12, but I don't get the 9. And there's lots of combinations of these that you can do. This could be a really useful way, for instance, to take a large list and to split it in half. That you could take the first half by doing colon and then the middle index of the list, and then you could get the second half by doing middle index of the list, colon, nothing else, and square bracket, to get the second half of the list. So these are really, really powerful ways to, in one line, grab a large chunk of your data. Another very powerful thing that you can do in Python that might otherwise take large numbers of for loops and if statements and things like that is list comprehensions. You can sort of think of them as a one-line for loop through a list that always creates a new list as its result. So, for instance, if you wanted to add 1 to every item in a list and get a new list that is that version where everything's had 1 added to it, you can do that with a list comprehension. And in fact, you can use a list comprehension to loop through any collection, like a range or a list, and as we go through the semester, we will see lots of other collections of data that you'll be able to use inside of a comprehension like this. So we start off with our list L, that is 4, 8, 12, and 10. You'll see eventually that there's a reason that I'm doing this. Then I say I want a new list L2. It will be equal to dividing x by 2 for each x in the list L. So you'll see this for x in L is sort of like a normal standard for loop over a list. But instead of doing a colon and doing all of the work after it, I actually state what the work will be before. And then I don't have to do something like create an empty list and add a new item to that list over and over again. What's happening is it's doing this x over 2 statement for each item that we name x in L. So you can think of it like a normal for loop still. So it's saying, first off, x is equal to 4. And then it's doing x divided by 2 and making that the first item in the new list. Then x is equal to 8, and it's doing 8 divided by 2 and making that the second item in the list. That's where the 4 here comes from. Then x is equal to 12, and it's doing 12 divided by 2, and that's why the third item in our list is 6. Then x is equal to 10, and 10 gets divided by 2, and that's why the last item in our list is 5. Because there are no more items in the list, this loop finishes, and we come away with a new list right away there on that line. Similarly, if I knew I was building a list using a range, for instance, here I've done the range 1 through 5, where 1 will be included and 5 will not be included, you may recall, and I'm squaring it. That's what the two multiplication symbols means, is a power. So in Python, I can do power of 2, or squaring, by doing times times 2. So I take each x in that range 1 through 5, that means the numbers 1, 2, 3, and 4, and I'm squaring it. So x is equal to 1 first, 1 squared gives me 1 as my first entry. Then x is equal to 2, 2 squared gives me 4 as my second entry. X is 3, 3 squared gives me 9, x becomes 4, 4 squared gives me 16, and then my range runs out of numbers, and so my list ends. And in that one line, I've gotten a list of the first 4 perfect squares. List comprehensions can be even more powerful if you want to have some condition on what goes into your resulting, or rather what gets used from your original list. This kind of filters down which values you're actually going to keep and do stuff with. So here, for example, I have again a list 4, 3, 12, and 9. We're back to our original list example here. And I make L2, where I say, I'm keeping x, just x, no x squared, no x plus 1, no x divided by 2, nothing like that. I can just keep x for each x in L if that x is greater than 5. So you might be able to imagine this coming out as like a 5-line for loop and if statement combination if we did not have comprehensions for it. But comprehensions allow us to say, all right, we're going to go through every x in L, but we only care about the ones where x is greater than 5. So let's step through the list this way and think about it like a normal for loop with an if statement embedded inside of it. So x becomes 4. And then we hit our if condition, and we see that 4 is not greater than 5. So we don't keep it. We don't do anything with it. That one's sort of thrown away, filtered out. Similarly, x becomes 3. And we see that 3 is not greater than 5, so we do nothing with it. It doesn't make it into our resulting list at all. Then we hit where x is 12. We see that 12 is greater than 5, and so we keep it. That x goes into our result list. Then x becomes 9. We see that 9 is greater than 5, so that x stays in our result list. And this has filtered our list down only to the numbers that are large enough for whatever our purpose is. We could do the same thing to eliminate negative numbers or numbers that are too big. For instance, someone tells us, here's the menu at my restaurant, and I know I only have $30. Well, in one line, I could narrow that whole menu down to the items that I can actually afford then. Similarly, I can do more interesting and complicated things with these if statement comprehensions, these comprehensions that filter or narrow down. So here, the thing I'm doing is I'm dividing x by 2, but I only want to do it for values where x mod 2 equals 0, or in other words, numbers that are divisible by 2, even numbers. So I'm taking L, 4, 3, 12, and 9. I'm going to go through each x in L, but I might throw some of them out. So x becomes 4. I see that 4 mod 2 is equal to 0. In other words, 4 is an even number. And I do 4 divided by 2. That's why the first item in my new list is 2. Then x becomes 3. I see that 3 is not an even number, and so I ignore it. I throw it out. Doesn't do anything in my result list. X becomes 12. I see that 12 is an even number, and so I keep it, and I do 12 divided by 2. And that's why 6 is the second item in my resulting list. Then I see 9. X becomes 9. And I find out that 9 is not divisible by 2. It's not an even number. And so I don't do anything with it. And I am now done with the list. There is no remaining data. And so all I ended up with was 2 and 6 in my result. So hopefully you've started to see that Python has structures for doing really interesting and sometimes complicated things with lists in pretty short amounts of code and hopefully clear to read pieces of code. It's also worth noting that in terms of speed, typically these built-in list functions and built-in list structures, like the remove function, the index function, looking items up by index in the list, or building new lists using comprehensions, these will typically be much faster than by hand code that you write to line by line. For instance, create an empty list and then do a for loop through an existing list and an if statement that checks each item in that list. Should I keep it or throw it out? Your code will typically be slower than these built-in Python structures. And that's not because your code is bad necessarily, but because these structures have been written to be very, very fast and very optimized. And so this is one of the ways where you can start to do things in Python in the way that the language was designed for. And as we get to other data structures, you're going to start to see that the language is designed to have these same kinds of structures for them that allow you to do powerful things in short amounts of code in ways that is very optimized and gives you the ability to think more about the algorithms, about the design, and come up with the ideas and make them a reality.